everyone. Thanks for joining and thanks for having me. Thank you very much. I don't know how to speak Korean, so it'll be in English. So if something is not clear or I should speak slower or something, just let me know. If you have questions as well, just raise your hand and I'll explain. I also don't know exactly what your background is, so I will first go through the general principles of aerodynamics, what simulations are, CFD simulations, what wind tunnel tests are. If I'm just repeating things that you already all know, just let me know and I can just skip through it faster. So, introduction, what are aerodynamics or what is aerodynamics? This is common for many applications that we see in day-to-day life. So you have a high importance of aerodynamics when it comes to transportation. Any object or vehicle that moves through the air has to push the air away. And you would think it's not really important, it's just air. Where's the resistance? But at high speeds, this becomes incredibly important. As we'll see, the aerodynamic resistance scales with the second power of your velocity, which means that the power required to move at a certain speed scales with the third power of your velocity. Which means if you double your speed, the power required goes up by a factor 8, which is huge. Which is why for airplanes, which are quite fast, this matters a lot. But we also see aerodynamics being relevant for buildings, the flow around buildings. You have regulations around the world that state if you build high-rise buildings, you need to study the way the air flows around the building at ground level, for example, so that pedestrians don't get knocked over if they go around the corner of a building. And of course the buildings themselves should be able to resist the wind loads. Also the glass on the buildings needs to resist. Energy, when I was driving towards the airfield, I saw many solar panels. More than 10 years ago, when I was still working as an engineer in a consultancy agency, more than half of what we did was to study the wind loads on solar panels because they can fly away. So we had to calculate how much ballast you should put on the solar panels or how much anchoring force you have on the roof so that they don't fly off. And of course wind turbines, that's their sole purpose, which is to capture energy from the wind. So obviously aerodynamics are extremely important there as well. In sports, so if you're a pro athlete and you're cycling, 80 to 90% of the energy that you're using is just going to waste to push the air away. So if you can be more streamlined, like with the special helmet, with special shoes, shaving your legs, all of those things, it matters a lot in terms of aerodynamics. Then the drones and the UAVs, which is one of the main topics that we're here today for, they can only fly if the aerodynamics work properly, and the payload, so how much weight you can carry, how far you can fly, all of those things are directly linked to aerodynamics. So crucial in that segment as well. And if you want to study aerodynamics, if you want to understand aerodynamics and improve the aerodynamics, there are multiple ways to do so, but the two main ways are the physical wind tunnel test, which is what you see on the left, and the CFD simulations, which is computational fluid dynamics, which is what you see on the right. There are other options. You can just go out there, you can take your car and you can do a coast down test, which means just let your car slow down and monitor how far you get or how the speed actually decreases and deduct from that what your aerodynamic coefficient is. You can do all kinds of experiments, but these are the main two methods. So, does it matter? So it depends on speed and more. So in this graph, if you look at a car driving, you would see that there are multiple forces acting on the car, which is why you need constant energy to keep moving forward. So the mechanical resistance, this graph is a bit simplified, so if I use the pointer here, let's see. So this purple line here is the mechanical resistance that you have to overcome to maintain a fixed speed, for example, when driving a car. Now, the mechanical resistance is quite constant. It's not exactly constant, but the resistance force is almost the same, whether you're going 10 kilometers per hour or 100 kilometers per hour. Now, that's the force. That's not the energy you need, because the energy you need to overcome that force is the multiplication between the force and the velocity. So obviously, the energy you need to overcome the mechanical resistance does go up linearly, but the force itself is nearly constant. The aerodynamics force, on the other hand, is not constant. As mentioned, it follows the square of the velocity. So if you double your velocity, you have a factor 4 in terms of aerodynamic resistance force. So that's really quite significant. If you then go to the next point, if the force goes up via the square of the velocity, the power goes up via the third power of the velocity. So a very simple example. On the left, I should have taken a Hyundai, but this is a Volkswagen Golf, which is just a normal compact car. It has around, or you can buy it with around 125 horsepower. And if you don't have any traffic and no police close to you, or cameras in Korea, many cameras, you can do maybe 200 kilometers per hour with this car, using 125 horsepower. On the right, we have a Bugatti Veyron. By now, it's almost 20 years old, around 20 years old. It could do 400 kilometers per hour, which was like a very big thing in the automotive scene. And to achieve this, it needs 1,000 horsepower. So just to double your top speed, you need 8 times as much power to actually achieve it. And that's just how important aerodynamics are for vehicles. Not just for supercars, but also when you're driving on the highway, around 70–80% of the energy that you need, or the fuel that you're burning, is just there to overcome aerodynamic resistance, just to push air away. So that's just to show how important aerodynamics are. When we look at aerodynamic forces, we can make a distinction between the friction force. So if this is my surface, the friction force is the force parallel to the surface. So literally, if I would slide air across the surface, the resistance that I feel is what we call the friction drag. Now, if I would just move my hand through the air, I would feel the air pressure. So when you're driving home later today and you put your hand outside the window, the force that you feel directly on the surface of your hand is the pressure force. So that's the force perpendicular to the surface. So very simple definition. One is parallel to the surface, one is perpendicular to the surface. Now, these two components, they vary in terms of importance. So if your object is very streamlined, the majority of your drag will be determined by the surface friction. You can imagine if you're flying an airplane through the air, it's very streamlined. So it is designed especially in such a way that you're not really pushing the air forward, but you're kind of cleaving through the air. So that means most of the drag is coming from the air sliding along the sides and along the wings of the airplane. Which is why on planes, this is a very rough indication. It can vary drastically depending on the plane, but maybe half of the drag is the friction drag and the other half is maybe the pressure drag. Of course, it depends a lot on the plane. But if you look at cars, cars are not aerodynamic at all. Of course, we're doing our very best to make them as aerodynamic as we can, but you have the exposed wheels, you have mirrors, you have a radiator, you have the rear of the car, which is just chopped off, you have the exhaust system on some cars. That means the pressure drag is the most important form of drag on cars, because it's just a block pushing through the air. It's a very square thing with a very bad aspect ratio, and it's not as streamlined like a plane. So on cars, the pressure drag is the main thing. Then if we look at drag coefficients, so a drag coefficient is a number that indicates how streamlined an object is irrespective of the size and the velocity. So whether it's going slow or fast, whether it's large or small, this number indicates just how slippery the object is through the air. And this number, the CD, the drag coefficient, allows you to calculate the actual drag or the actual air resistance on your object. And to do so, you need to take that size and that velocity into account, plus the density. So what we see is that we need half of the density multiplied with the square of velocity. So we saw before that aerodynamic forces, they scale with the square of velocity. That's what you see here. We multiply it with the drag coefficient, which is how streamlined an object is. So the higher the drag coefficient, the higher your force will be. And we multiply it with the frontal surface area. The frontal surface area is when you're looking at a car, at the front of the car, if you make like a contour around the car, like a 2D projection, that area is the frontal surface area. Keep in mind that if you look at airplanes in aviation, we have a similar definition for the drag and the lift on an aircraft, but instead of using the frontal area, which is what we see at the front of the car or the airplane, we'll look from the top, which is what we call the planform area. So you would see like the contour of the wings and so on. That's the planform area. Now, just to give you an idea, here are some numbers. They're probably too small to see, but if you have a sphere, you would be around 0.5. But again, keep in mind, a drag coefficient is not constant. We'll see this later on. This, again, depends on size and velocity, basically on the Reynolds number. But for now, the simple theory states that you have a constant drag coefficient, and you can use it at different speeds and sizes. If you want like a very streamlined object like this one, which is like a drop-shaped body, it would have a drag coefficient of around 0.04. Now, just as a reference, over here you can see that modern cars, they are anywhere between 0.2 and 0.35. That would be your typical car. If you'd go to like a pickup truck, you would be even higher, but most of the sedans or small cars would be in this range. If you would have a truck, especially if it's not optimized for aerodynamics, especially when your cargo is open, when I was coming here, I saw trucks with frames or tubes sticking out, then you would be very high in terms of drag coefficient, maybe 0.5, 0.8, so it can be quite high. So the Reynolds number. So we saw that a drag coefficient in theory is constant. In practice, it actually can change depending on the Reynolds number. Now, what's the Reynolds number? Basically this definition. So it's actually the ratio of, at the top we have the inertial forces, which are related to the speed and the size of your object, divided by your viscosity. That's what we see here. Now, what does this mean? So the bigger your object and the bigger your speed, the more the inertia, like the force needed to accelerate or push air away, becomes dominant. And the higher your friction or the viscous forces at the bottom, the more the air actually resists motion between layers of air. So the friction, like we saw, the friction on the surface, you can also have friction between the layers of air. So if the air is moving fast here and slow here, that means you have a velocity gradient, which means the layers of air are sliding on top of each other. And this is generating friction. And if you have a highly viscous liquid, you will have a lot of resistance that you need to overcome to actually set the air in motion. And as you can imagine, the one at the top indicates how much the air wants to move around, and the one at the bottom indicates how much the air is actually slowed down or put back into a normal, orderly way of moving. So if you have a high Reynolds number, you will start to get oscillations, you will get to start to see turbulences in your flow. But if you have a high viscosity, you will get a lot of damping, which actually takes away the viscosity, the turbulence again. So that's at least my way of understanding the Reynolds number. If it's very high, you'll see a lot of oscillation and motion in the air. If it's very low, because there's lots of viscosity, for example, or because you're just going slower, there's a lot more damping, which can calm down the flow. Not a perfect definition, but for me it works at least. Also, the Reynolds number is not a real physical quantity. It's not like the velocity or the entropy or something. It's some kind of indicator or a ratio that we use to just quantify where exactly an application is in terms of Reynolds number. If you want to compare the wing of an aircraft to the wing or the blade of a turbine, typically people would say, but it's a different Reynolds number, so you'll probably have a different flow regime. Talking about flow regimes, what we see here is the difference between laminar flow So laminar flow is where all of the streamlines, if you would just look at one particle traveling along with the air, if that particle just follows the mainstream of the airflow nicely, now this is what we call laminar flow. It's not moving around in all directions, it's just following the overall flow going along with the mass. Now, if you have a flow through a tube, for example, like what you see in this case, and you see that the flow is going in all kinds of directions, the averaged flow is going forward, so you still have a mass flow, a net mass flow going in one direction, but if you would zoom in on that flow, you would see the air or water particles going in all kinds of directions, superimposed on this averaged flow. And that's what we call turbulent flow. It's very nervous, the flow goes in all kinds of directions. And this has a lot of implications. For example, if you have turbulence, if you've taken an airplane and you experience turbulence when the pilot says we're going to hit some turbulence, you can suddenly like bump in the airplane. That's because turbulent air drastically changes the way an airfoil works when it is going through the air. So you can suddenly lose lift in an aircraft and it just drops down until you hit some laminar air again and you restore your lift. So when they say we're expecting turbulence, it means the lifting properties of the wings will change and you'll feel vibration in the air. This is also important when it comes to cars. Like across a car, from start or the front to the rear, the goal is to maintain laminar airflow. When you hit turbulent airflow, usually you increase the drag on your vehicle. So we want to maintain laminar airflow as long as we can, which is not easy on cars because when you have the wheels rotating, they act like a mixer in the air, and it's almost impossible to maintain laminar airflow around the wheels. You have the opening, which is the wheel well, which is where the wheel is located. It's just a cavity where the air is going around in all directions. On a car, you have a lot of small features like the gaps between the doors, the door handles, where your windscreen wipers are, the grille in front of the car. All of these things, they disturb the flow, which means that you create turbulence, which probably increases the drag. So that's why turbulent flow and laminar flow are very important topics to study. Another note on the drag coefficient that we saw is that we mentioned that a drag coefficient in theory is constant. So we saw this simple formula where you can just calculate the drag force or the lift force by multiplying the square of velocity with the frontal surface area and the drag coefficient. And now, just 5 slides down the line, I have to tell you, sorry, it's actually not true. It's true for simple theory if you don't change the velocity or the size too much. But in reality, if you would take a car and take it from 100 kilometers per hour to 500 kilometers per hour, it would drastically change in terms of aerodynamics for many reasons. If you would plot the drag on a sphere in function of the Reynolds number, now if you want to change the Reynolds number, we saw that it depends on both the size and the velocity. So if you want to analyze how the drag changes in function of the Reynolds number, you can change the size, but you can also change the velocity to do so. So if you put the same sphere in your wind tunnel there at the back and you double the velocity, you have changed your Reynolds number. If you would keep the velocity the same, but you would double the size, you would also change your Reynolds number. And if you want to play it really in a difficult way, you can also change the viscosity to change your Reynolds number. That's a bit more difficult because that means you need to change the air that you're using. You can heat up the air, which will change the viscosity and the density, but only by a small portion. We also have, we've done many interviews, one of them was with Airbus, and they have special wind tunnels where they use a different gas in their wind tunnel to change the Reynolds number. Because if you change the size of an aircraft, because a full aircraft is too big to test in a wind tunnel, if you change the size, you change your Reynolds number. And if you want to compensate for that, you can do so by using a different gas, for example. And this is part of a bigger set of equations, or let's say ratios that you want to keep the same, which is what we call the scaling laws if you want to do a scaled wind tunnel test. So keep in mind there are many ways to change the Reynolds number. if you look at the effect, this is the drag coefficient of a sphere in function of the Reynolds number. So we see here that if you go from a Reynolds number of maybe 100 or even less, the drag coefficient can be higher than 1, which is quite weird, right? Because 1 is typically what you would get for like something like a plate or a cube. So the drag coefficient can be very high on a sphere. If you start to increase the Reynolds number, you see that it goes down, and then at some point the flow regime starts to change. You start to get flow separation on your sphere, you get turbulence, the location where the airflow separates. So the airflow wants to stay attached to the surface, and then it becomes too difficult and it just lets go. All these things, they can change if you change your Reynolds number. And then we have a very funny aspect when it comes to the drag coefficient of a sphere. We can have what is called a drag crisis. So if the velocity is just right, the drag coefficient is actually quite low. And then it starts to go up again. And this is all a very complex combination of going from laminar to turbulent flow, separation locations changing, and so on. The main message is, yes, you can use a drag coefficient to compare different cars and airplanes and so on, but keep in mind, when someone states a drag coefficient, in theory, you have to ask them, yes, but for which velocity and for which size? And in theory, was it air or was it another gas? Just as a reference. If you look at an airfoil, so we're here today to talk about aviation applications, the funny thing is that no matter how smooth a surface is, the air will always stick to it. So that's a bit counterintuitive, right? You would think if I have a perfect surface finish, the air will just slide nicely across, which is true to some extent. But if you zoom in, at the surface, the velocity is always 0. If you have a high roughness, of course, this will impact what happens just outside the surface, but on the surface, it's always 0, which is what we call the no-slip condition. Which is what we will also see in simulations, such as no slip condition on the surface is being applied. So that means between the free airstream, which is the velocity of the air approaching your wing or going around your wing, and the surface, you have a velocity gradient. So that means somehow the velocity needs to go from 0 to the free stream velocity, and in between you have a velocity profile. And this velocity profile is really important. This is what we call the boundary layer, which we'll look at in the next slide. So if you would have air just coming onto this table. So imagine this is a very sharp point. We don't have any weird effects at the beginning, just a sharp point like we see here at the beginning here. The air would start to stick to the surface, and this generates friction. So this first layer of air close to the surface starts to slow down. Because that layer starts to slow down, the rest of the air starts to surf on top of that layer. And then that air also starts to slow down. So the more you travel along this table, the thicker this layer becomes. And this is what we call the boundary layer. It's a layer of slow-moving air sticking to your surface. And of course, you can influence this. If you have a smooth surface or a rough surface, this boundary layer growth and thickness will change. And at some point, what can happen is that the boundary layer starts as laminar. So we saw laminar flow is nicely parallel streamlines. And at some point, it becomes too much and it starts to become a turbulent boundary layer, which features all of these turbulences that we saw before. And this velocity profile that we saw is different for a turbulent boundary layer compared to a laminar boundary layer. So if you're looking at cleaning up the airflow around the wing, for example, controlling this boundary layer is one of the key things to reducing drag. Also, when you're removing your flaps to come in for landing, you want more lift. You still want to maintain laminar flow as much as you can. So if you start to research that field, it's really interesting to see how the openings between the flaps on an aircraft, they're super crucial. Without those, it wouldn't work, because those flaps, they feed air into the pressure, suction side of the wing and so on, all to maintain attached airflow as long as we can. this is where we get to attached and detached airflow. We get the question very often to let our customers know if adding dimples will reduce the drag on their vehicle. And we fully understand this. Like the one example to reduce drag that people know is just add dimples. Just add dimples on whatever you see. Take your car, just smash some holes in it. Unfortunately, it doesn't really work this way. So why do we have dimples on golf balls? By the way, if I'm going too slow, let me know. Do we stop after 1 hour, or we can go a bit longer, or can be a bit longer than 1 hour? Or? Okay, okay, fantastic. So a golf ball is a sphere. So we just saw that curve of a sphere. What is the drag on a sphere? And it can be quite high, depending on the Reynolds number. If you want to reduce the drag on a golf ball, what you can do is to work or control the boundary layer. So when the air hits the front of the golf ball, we saw like just on this table here, if you move long enough across the surface, the boundary layer will become thicker and thicker and thicker. So it starts to move slower. And at some point, there's not enough momentum in the boundary layer to still follow the surface, and it will let go. The flow will let go, which means you have detached flow. So the flow at the top will stop to follow the surface here and then just go straight. At the bottom it's the same, which means in between you have a wake, which is a messy area full of turbulence and separated airflow, and this is pulling back or holding back the golf ball. Now, if you want to reduce the drag, you can actually make the boundary layer turbulent. So as we saw, turbulence is like a nervous motion of the air inside the boundary layer as well, and this gives the air more momentum. And if you have more momentum, the air is able to stay attached or follow the curvature of the golf ball for just a bit longer, which reduces the size of the wake here behind the golf ball, and this actually reduces the drag. Now, if a golf ball would always be flying forward with the same point pointing forward, we wouldn't have to cover the entire golf ball with dimples. We would just have to cover some of the locations here just ahead of the flow separation. But because we don't know what the orientation of a golf ball is, we just put the dimples everywhere. So whatever the orientation of a golf ball is, it'll just be working. Now, as we've seen, this is a tool to solve a situation where the laminar airflow is no longer able to follow a curvature. So on older cars, the curvature would actually be very bad. You would have like the Mitsubishi Evo, which is like a rally car, which would have a very steep rear window, and you would have vortex generators to force the air, please stay attached down the steep rear window. So vortex generators and golf ball dimples are a way to make your flow more energetic and follow the curvature. But the best way to reduce drag is to just have a curvature of your car which is smooth enough so that even the laminar flow just stays attached. And then you don't need vortex generators or golf ball dimples. So they're just a tool to fix something which is actually bad in the first place. It can be useful, sometimes there's no way around it. Even on large airplanes, they still use vortex generators sometimes to modify the stall and so on. But in theory, or in principle, you don't really need them if your design is good to begin with. So flow separation, we'll look at why this happens. I'll not stall too long here. So the airflow just follows the flow around the cylinder, for example. It accelerates, but then it decelerates, and actually your pressure gradient changes. You can get reverse flow here. I'll not spend too much time on this one. We can actually get a main flow across the surface, but then at some point there's flow curling back underneath the flow, and you get flow separation, and then the main flow starts to surf on top of that little thing, and that gives you flow recirculation here, and this becomes a separated airflow. Now, if you look at CFD simulations, how do they actually work? Well, we can look at very simple problems like the flow around the cylinder, and we can come up with analytical equations where the equation really solves your problem, a direct link between the input and the output. But as soon as it becomes more complex than a cylinder, we don't really have a solution. We don't have a mathematical equation for the flow around the car, because the car is just way too complex. So what we do instead with CFD simulations is that we, just like taking a picture, if you would take a picture of this coffee here, I think it's coffee, you would have a certain resolution. And to distinguish between the cup and the background and small features, you need enough resolution to distinguish between the different features. The more pixels you have, the more detail you capture. With CFD simulations, we do the same. So we divide reality into, let's say, pixels, but they're actually 3D pixels. They're blocks in space. Sorry. So they're blocks in space, which is what we call cells. You can think of them as 3D pixels. So every single block in there, which is a cube or like a pyramid shape or something else, depending on the measure that you're using, for every single one of those blocks, we can solve simple equations. And if you put all of these equations together into one massive matrix that you then need to solve, you can actually solve the flow across your object. Now, CFD simulations are always wrong. Wind tunnel simulations testing is also always wrong. But it's a matter of knowing just how wrong they are and to know which parameters influence the accuracy of your simulation. So definitely keep that in mind, that they're both wrong. They're always wrong. But you have to control or at least know what is causing inaccuracies. So we've seen that we are going to apply equations to those small blocks and then solve them. And this is a set of millions and millions and millions of equations just to solve one case. So there are basically 3 errors that you can create in CFD simulations. The first error is what we call the modeling error. So I mentioned that we're going to solve equations. Well, those equations, if the equations are wrong, then of course you're going to get an error in your simulation result. Or if you're not taking enough equations into account, you will also introduce an error. Now this may sound trivial, but we have momentum equations and so on, of which we think that they're pretty accurate, pretty correct. But then if you go to a simulation where maybe one part of the car is slightly hotter than another part of the car, if you don't take thermal effects into account, because if one part of the car is hotter than another part because you have an engine underneath, it slightly changes the density, the viscosity, and so on of the car, which can change the airflow. Now, if this effect is minor, you can just ignore it, but you're introducing an error because you're not taking a certain physical equation into account. Electromagnetic fields, all those things of which you think they're not related to aerodynamics, well, in some cases they are. So if you don't take them into account, you're introducing a modeling error. So modeling errors, the equations you're using could be wrong, and the equations that you're not taking into account are also introducing an error. The second thing is the discretization error. I talked about the resolution of your photograph if you want to distinguish between small features. It's the same with a 3D model. So if you're creating a mesh, so a mesh is this combination of all those small blocks in space. If your mesh is very coarse, so you have very big cells, you cannot expect to capture like a small swirl like this if your smallest cell is actually bigger than the thing you want to see. That's impossible because every cell has just one component of the velocity and one pressure value. So if you have a block like this and you have one velocity component, you can never capture a swirl like this inside this block. So you need enough mesh resolution to capture your flow properly. And also, when you're solving those equations, you actually make a discretized version of the equation, which is taking a mathematical equation and then making like a version of it which can be solved using the cells next to you. And this is what we call a discretized version of an equation. So the resolution and the modified version of your equation to work with those blocks is what we call the discretization error. Then, once you have all of your equations, so for every single cell, you've build your equations, and all of those equations are linked to each other. Because what happens in this cell is linked to what happens in this cell, but also the other way around. And every single cell is directly or indirectly linked to each other. So that means if you want to solve all of these equations directly, it can take a long time, a very, very long time. So what we do is to start with like a guess of the simulation results, and then we iterate. We start with a guess and we start to correct, like, oh, my velocity is 10, then you cannot have 20, that's too big of a difference. So we start to iterate until we find, like, let's say an equilibrium or a converged solution for your equation. And you can decide to stop after maybe 100 iterations, or maybe after 1,000 or 10,000 iterations. So if you cut too soon, you will introduce a large error. If you cut after a very long time, you will have just a small error, but maybe you're just wasting time in computational capacity, which means time and money. So 3 big categories of errors for CFD simulations, at least for this finite volume approach. So keep that in mind. And it's also important that you don't spend too much time to reduce one error if you know that the other error is still 10 times larger. Then you might be better off trying to reduce another error. Just some cases, I will dive into some demos later on. If you look at physical wind tunnel testing, as mentioned, both are wrong. So let's see at why wind tunnel tests are wrong and just by how much. So how does a wind tunnel work? It's basically a tube, which can be an open tube, like the one you have in the back there, or it can be a closed tube where you recirculate the airflow. Both have their advantages and disadvantages, but in general, the benefits of a wind tunnel are that you're working with real physics. So you're forcing real air across your object. So whether you have a very small feature, which you would not capture with your mesh maybe, you will still have airflow interacting with it in the wind tunnel. So that resolution aspect is actually less critical. Also, you can test many different variations of your object in a very short amount of time. So imagine you're doing testing on an airplane and you want to analyze the lift and the drag of your aircraft for different angles of attack. You can just put the airplane at one angle of attack, measure for 30 seconds, make a nice average value, put it at a different angle, repeat, 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 repeat. So you can easily come up with 50 test data points for an aircraft within an hour, for example, if you've prepared everything well. That's really nice. In simulations, that would mean 50 individual simulations, which can, of course, become more costly and time-consuming. Another benefit is that it can be very accurate. If your model is accurate and your wind tunnel is a very good one, you can actually get very accurate results. One of the key challenges in Formula 1, for example, is to find a good correlation between your CFD simulations and your wind tunnel test data. Because once you have a good correlation, then you can be quite confident that whatever you do in simulations will actually be true in the wind tunnel and hopefully on the track as well. Perhaps as a side note, one of the challenges in Formula 1 2-3 years back for Mercedes was that the car was very nervous, which was called porpoising, because something was happening with the flow underneath the car. And apparently this was related to the fact that the moving floor in their wind tunnel was not entirely the same as what you would get out there. So in the wind tunnel, the car was doing fine. In reality, because the wind tunnel is not the same as reality, it started bumping around everywhere, and this had an impact on their performance. Downsides of a wind tunnel, you do need a model. So imagine you're designing an aircraft and you want to test it in the wind tunnel. Well, you need to build your aircraft. Which means if you're in the early stages, you need to make a prototype. Making a prototype is doable, but it's expensive and time consuming. So you need to build it. Again, we run into the same issues that we saw before. An aircraft is very big, so if you want to scale it down, you also introduce scaling errors in your wind tunnel campaign. And you're not seeing the air. So if you want to get data or insights out of your wind tunnel tests beyond the forces that you measure, so of course you can measure the forces and the pitch, roll, and yaw moments, but if you want to see or understand what is happening, you need special techniques. Like a very simple one is just release some smoke and you'll see what's happening. More advanced methods include laser measurements and so on. And it can be very, very costly. A wind tunnel, if you just want to have a very basic wind tunnel, and my reference is European prices, it's probably different all over the world, but when we did some wind tunnel tests in the past, it will probably be like 5,000 euros for one day, and this is 10, 15 years back already, for a very simple wind tunnel with a cross-section of maybe 2 meters without any moving floor or anything. If you go to automotive and you want a moving floor, it's more around 5,000 euros per hour to rent that wind tunnel. So these things are very, very expensive. How does it work? Well, so the one you have in the back there is what we call an open wind tunnel, which means you're drawing air in at one side and you're spitting it out on the other side. The downside is that this is not very energy efficient, because every time you have to take standstill air, accelerate it, and just spit it out, and the energy is lost, right? The good thing is that you always get air of kind of the same temperature. So if you have a closed circuit, that air goes around and around and around, and all that energy that you're putting in the air to overcome the friction and to maintain that speed gets converted into many things, but also into heat. So the wind tunnel can start to heat up the air, which, as we saw, influences your density and your viscosity, and so this can bias your results. So then you need to add cooling to your wind tunnel. But let's focus on the closed loop wind tunnel. So what we see is that we have a test section. This is the part where you put your airplane or your car to test everything. So there you'll have like a force balance to measure the forces, your laser system if you have one, your moving floor, and so on. So somewhere else in this loop you need a fan, something to drive the flow. And the fan will create a lot of turbulence, will create a lot of problems with the flow. But what you want on your model is a clean flow with a uniform velocity distribution. You don't want that in the center velocity is 11 meters per second and at the sides it's maybe 9 meters per second, because that's not what you have in reality. So this uniformity of the flow and to take away the turbulence in the flow as much as you can is really quite important, or to at least have the right turbulence value. So your fan is usually quite far away, and to go around the bend you have what we call turning vanes. So these are simply just corners, sheet metal corners in many cases. They help to turn the air to not lose too much energy and to not introduce too much turbulence. Then what we have, after going through the corners, the air will go through what we call a honeycomb and screens. Yes, honeycomb and screens. So these are just very small tubes to take away the lateral motion of the air. So if this is the overall airflow, like we saw, turbulent airflow is doing like this, superimposed on the flow. If you want to go through this honeycomb, you're being forced to go in a parallel way. Now, after you have exited this, so here you can see that it's not the best illustration, but I drew a line showing that if you come in at an angle, you just have to come out in a horizontal way, because every tube is parallel. So this straightens the flow. Now, you can still come out at a different velocity in different locations. So to equalize the velocity, it's actually a very simple method. We have a screen which is just introducing resistance to the flow. Now, if you introduce resistance, this is a non-linear effect. So if you want to move through this screen, your resistance go up by the square of the velocity, also again like we saw before. So that means you get penalized a lot if you're going faster than your neighbor in the air. So that means you're being slowed down. If you're going too slow, well, you don't have much resistance, so you can easily speed up. So this equalizes the velocity. So we want to make the flow parallel, nicely parallel, and to have the same velocity everywhere. And then what we have, after we've exited this system, we will contract the flow and speed it up to the velocity that we want in the test section. Now, a number of challenges in your test section. So at the beginning of your test section, your plane or your car is not there. So you have the same velocity everywhere and the same cross section. So the cross section is the area that you would calculate if you do like the width times the height, that's your cross section. If you put a car in there, that is no longer your cross section. So if you put a car or an airplane in the wind tunnel, the airflow has a smaller section through which it can flow. So that means the airflow has to speed up, because the air that goes through this cross section at the beginning also has to go through this cross section, because there's no exit from the tunnel. So to conserve the same mass, you just need to go through a smaller opening, which is this opening. So the same cross section minus the car, which is actually blocking your flow. So that means the air speeds up, and the average airspeed is actually higher than what you had at the beginning. So if at the beginning your airspeed was 10 meters per second, it'll be maybe 11 meters per second by the time it goes around the car. So that means if you calculate the forces, you should not do it relative to 10 meters per second, but relative to 11 meters per second. And this is what we call the blockage factor. So the blockage factor is actually the surface area of your car relative to the cross-sectional area of your wind tunnel. So if your car is blocking almost the entire wind tunnel, this speed up will be very high, and you have a very high blockage factor, which again introduces errors in your flow results. So a typical rule of thumb, and this is not a hard limit, but is to keep this below 5, max 10%, this blockage ratio. So that means if you want good, reliable wind tunnel results, you need to rent a very big, expensive wind tunnel for a small object. Other effects in the wind tunnel are what we call wall effects. So it's one thing to have a low blockage factor, but if you have like an object like an airplane, the frontal surface area may be small, but it's actually very wide. And the wings can be, if this is the wall of the wind tunnel, if my wing is over here, the wingtip is a very important aspect in terms of aerodynamics, which means that the flow around the wingtip really extends quite far beyond the wingtip. Now, if the wingtip is too close to the wind tunnel wall, the wall will block this effect. And this really has a strong impact on the behavior of your aircraft. Suddenly, you will think that you have maybe 100 kilograms of lift, but in reality it might be 80, because maybe your wall of the wind tunnel was blocking the wingtip vortex, which actually increases your lift. So you have to watch out with this. And there it's interesting to just run a simulation with and without the wall of the wind tunnel next to it, just to see what the effect is. Then we talked about scaling issues. So the thing is that if you want to keep the same Reynolds number as we saw before, because if you change the Reynolds number, you can change the drag coefficient that you measure, and it's not representative. If you want to keep the same Reynolds number, you can see that if you change the size, which is the length in this formula, if you cut the size in half, you need to double the velocity to maintain the same Reynolds number. Or, as we saw, you need to change the viscosity or the density, but that's more difficult. So you're left, for most wind tunnels, only to work with the velocity. Now the funny thing is that if you have a Formula 1 car and you scale it down by a factor 2, that means you need to double the velocity. That's fine, but not every wind tunnel has the capacity to just double the velocity. Imagine you want to predict the performance at 100 meters per second for your race car. That means 360 kilometers per hour, and they actually hit those speeds almost. If you want to use a scaled model, because you want to use a smaller wind tunnel, that means you need to go to 200 meters per second, which is 720 kilometers per hour. That is not only very expensive and very difficult to achieve, this also puts you into the compressible regime of airflow. So anything beyond max 0.3 or 360 kilometers per hour, it's not like an abrupt change, but beyond that speed, you start to see the effects of compressibility. So the more you go beyond a certain velocity, or max 0.3, the more the compressibility effects start to play. And those are just almost impossible to compensate for. So keep in mind that if you work with scaled models, there's a lot that you need to compensate for. To measure things in the wind tunnel, as mentioned, you can measure forces. So what we see here is an airplane which is being held by a force balance. So what this thing does is to measure the XYZ forces, so lift, drag, and lateral force, especially when you do a yaw maneuver with your plane, you'll get a lot of lateral forces. But it also measures the moments, so the pitch moment, which is up and down like this, where you come in for a landing or something. The yaw moment is when you go sideways. If you're flying in side wind, you have to compensate a bit. You also have the roll moment, which is along the longitudinal axis of the aircraft. So this can all be measured, but keep in mind, of course, your measurement equipment can introduce errors. Nothing is infinitely accurate. And the measurement equipment itself is also part of the aerodynamics. So if you hold your aircraft like this, you're impacting the airflow on your aircraft. So that's why this arm here is also an airfoil, to be very streamlined and not have too much impact on your system. Same for a Formula 1 car. This one is actually being held slightly above the ground so that the forces are acting on this arm, this connection part. And again, you see that this is a very streamlined part to not impact the airflow too much. If you want to measure pressures locally on a surface, that is one of the benefits of simulations. There you can just point to a location and ask the software, give me the pressure on this point. If you want to do this on a physical prototype, you need to actually drill a hole, connect the cable, or put a pressure sensor there, and then send all of these cables to a pressure transducer to measure and log all of the pressures. Quite time consuming and complex and expensive, but you're working with the real air. I mentioned lasers. You can also do laser measurements, which is a laser will highlight like a 2D plane, and then you look at that plane from a perpendicular direction with the camera, and then you monitor the changes in position. Quite a complex technique, but it allows you to actually create a velocity pattern and based on that, or linked to that, calculate the pressure distribution. Now, what we do at Airshaper is that we have automated CFD simulations in the cloud. You saw that there are many aspects to creating a CFD simulation, and I only highlighted less than 10% of what it takes to run a CFD simulation. So it's fun. I would definitely recommend learning it yourself, but it's very time consuming and complex and difficult to get it to work stable. So what we did is we automated this process in the browser to that extent that you don't actually need CFD simulation knowledge to set up a simulation. So what you see here is an example of, this is the Archer Midnight, which is an eVTOL, but just a public model to illustrate this. We can work with models which are not watertight. Normally, if you have a 3D model, you need to make sure that every single gap and hole in the model is closed. Otherwise, the CFD software usually crashes. So that alone usually takes you days or weeks to solve. You can see that we have many components here. We've made our platform compatible with up to 10,000 individual elements in your model. We've made an intuitive interface to select rotors and so on. You can just toggle whether your aircraft is taking off or is in the ground. You can calculate ground effects. You can change the angle of attack here. We also have companies like PAL-V, which is a flying car. They're using a combination of rotors and radiators to cool the airflow while they're flying. That's all possible. And after this, everything is automated and gets pushed to high performance computing, which means servers with much CPU, very high CPU power, more than 100 CPUs, more than a few hundred gigabytes of memory, to get the results to you within a matter of just hours. So what you see here is a visualization of, now it's pressure on the surface. So you can see the suction side on the propellers. You can see the high pressure on the support arms of the propellers, and so on. The surface friction and streamlines, they show you how the air flows around the surface, where you're actually having a high friction component of drag. You remember that we saw pressure drag, friction drag? That's what we see here. These are the streamlines of the air being pulled down and accelerated by the vertical lift propellers. This is a rough noise estimation, and here we automatically calculate all of the performance characteristics of the propellers. So we can calculate the efficiency, the thrust that they provide, the power that you need to operate the propellers, and so on, all in a fully automated way with just 5 minutes at a time. Now, we're not aiming to replace any CFD software out there, what we aim to do is that we can accelerate the time to market. Because many companies don't have the resources to buy a license, which is typically more than 50,000 euros. If you want to buy ANSYS, of course, for now you can buy academic licenses, but once you get out there in the industry, it becomes very, very expensive. Plus, you need someone to work with those simulations, someone like you, and I hope for you that you will get paid well in the industry. But if your manager looks at your wage and sees, oh, that's an expensive person, well, this all adds up to the cost of running CFD simulations. Plus, you need your own hardware. When I mentioned that we use more than 100 CPUs for one single simulation, if you buy such a machine, just ask some other people in the room, that's expensive. It pays off if you do this every day, if you're an automotive company. But if you're a smaller company, or you just want to have a parallel solution to your precise but time-consuming workflow, you can use Airshaper to get accurate results just in a matter of hours. So that's our business model. We help many companies to really get into aerodynamics and get there fast and in a reliable way. How we do this, that's what I'm going to explain now. So one of the things that we developed is what we call adaptive meshing. Now, we didn't invent the concept. This exists out there, but we developed it specifically for OpenFOAM, which is the open source library that we use. And we also made it open source. So if you're working with OpenFOAM, just head to our website or drop me an email. I'll send you the link. Our version is a bit more complex, but the one that we made open source is available to do adaptive mesh refinement. I'll not dive into the details, but we talked about these blocks, those 3D pixels, which we call cells. Of course, you want to have them as small as possible everywhere, but that's just too expensive. So what we do with meshing is that we make them smaller where it matters most. So if you look at the flow around this coffee cup, when the flow is still here, not much is happening. It's just normal laminar flow, just all parallel. It's only when it gets to the cup, it starts to deviate, there's turbulence and everything. That's where you want smaller cells to capture more detail in the flow. So that means you can refine locally, but what we mean with adaptive mesh refinement is that we first run a simulation where we already made the mesh smaller, close to the cup, because we just know based on experience it's going to be interesting there and we need the mesh there. Once we've seen the flow results, our algorithms will automatically make the cells even smaller locally where the flow is actually struggling. Something we don't know up front, but if you have, for example, a vortex here or some turbulence here at the bottom, our software will pick this up and then locally refine the mesh, which is what we call adaptive mesh refinement. Basically, it comes down to making the best possible use of the number of cells that you have available. Because number of cells means more CPU, more memory, which means higher cost and longer waiting times. This is an example of the result. This is a slice through the mesh. So we saw that we have a 3D wind tunnel, which is like a volume. So now we're slicing through. Here you can see that we can have mesh on the inside. So our platform is compatible with mesh on the inside of a model. You can see around the propeller here that the mesh is more refined. And you can see in the wake here, so this big stream behind the aircraft also got more refinement. We didn't do this manually. This was done automatically based on the flow result because the algorithm detected that there's a high vorticity in the wake, so refine the wake. And there's a high pressure gradient around the propeller, so refine the propeller locally. So when we have a mesh of 10 million cells, it's roughly the equivalent of maybe a mesh of 20 million cells that you would make manually. Because when you make it manually, you just refine an area, but you don't know exactly which area needs to be refined most precisely. Plus, it's very hard to refine the mesh in 3D based on your input. We also refine the surface mesh. So you have the volume mesh, which is those 3D pixels in space. But we also have the surface mesh, which is how they connect to the surface that you're trying to analyze. So here you can see that when you have a landing gear, for example, the mesh was refined because there the airflow hits the landing gear, turbulence, more vorticity, more pressure gradient, and so on. So we got a refined mesh there. You see that the propellers are very detailed And then you have areas in between where the airflow is nice and laminar on the fuselage. There we have a less dense mesh. To model the behavior of propellers. So there are many ways to simulate the behavior of an aircraft. We can make a distinction between steady state simulations, which means it's a fixed position, a fixed flow pattern. If you would look at the flow for like a minute and take the averaged flow, that is what we call steady state simulations. If you look at transient simulations, that is where every fraction of a second you look at the flow and you will see the changes in the flow the whole time. If you have a flow around this cup, for example, if you have turbulence at the rear or in the wake, you have vortex shedding, the flow structure changes the whole time. If you're driving in your car with the window open, you hear this thumping sound, that's because you have changes in flow, changes in pressure. That's what we call transient flow. We run steady state simulations, which means we don't analyze the flow every single fraction of a second. We can, but it's more expensive. It takes a lot more computational effort and storage to do so. So we run steady state simulations, which means our propellers don't really rotate. Now, to still get the effect of a propeller, the thrust of a propeller, like we actually saw the effect of a propeller in our flow, we use what is called MRF, which is moving reference frame, which is a region around your propeller, and inside that region, you remember that we talked about modeling, the right equations and so on, we will add additional equations in that area to solve for the centripetal forces and Coriolis forces, which allow you to actually calculate the thrust without actually having to move the mesh. There are many different aspects to this. The size is important. The way you stay away from static elements is important. So we've developed a technique that automatically grows this region around the propellers, but then still stays away from any static components cutting through. Because if that happens, your results are unreliable. So this is also one of the things that we implemented to automate everything, still have very high accuracy, but not have to ask the user, hey, please make these cylinders, because the user typically doesn't know or doesn't have time to solve it. Another thing that we implemented is what we call convergence monitoring. So we saw that you can run your simulation for 100 iterations, 1,000 iterations, or 10,000, and the longer you run, the more it costs you. So you have to find a balance between not stopping too soon or too early, because then your result is not accurate, and not stopping too late, because then you just wasted computational effort. This is what we call convergence monitoring, what everyone calls. We didn't invent this, but we created our own library for this, which is also open source. So what happens is that, imagine you have the force on your airplane. It's going up and down and up, and then it starts to get stable. Then we would say, oh, this simulation seems to be stable. Let's start averaging the flow, which means continue the flow for a number of iterations to just filter out all of those oscillations and then stop the flow. And then we would stop the flow, but what can also happen is that it's temporarily stable and then it goes up again, which means we detect this and then we just have to restart the process. So if we restart the process again, imagine the yellow window is where we evaluate stability. At point B, we have determined, okay, the simulation is now stable, the forces are stable enough. And from that point on, the green window, up until this green dot, is the extra number of iterations that we perform to get a reliable average value. And sometimes we continue for just 200 iterations if the force is very stable. And sometimes we continue for 2,000 iterations if we see that there's a lot of nervousness and we just need more data to filter out these oscillations. This is a typical example of a real simulation. So you can see that it comes from very low, forces go up, start to oscillate, and then here we determine, okay, looks stable, and then we continue the simulation until the average value is reliable. Again, an example of the drone that we saw. Just to show, this is what we call the pressure clouds, which is an isosurface of total pressure, which allows you to understand where you have flow separation. So here the wing is installed. The landing gear is causing drag. So all of these things can be analyzed with an isosurface of the total pressure. The surface friction, so perpendicular to the surface, will show you that you have lift on the top of the wing. You will see pressure at the leading edge, this red here, at the beginning of the wing here. That's your leading edge where the air hits the front of the wing. And then we'll see that at the bottom of the propeller blades you have a high pressure because they're pushing the air downward. At the top of the propeller you will see a low pressure, which is the suction side. You will see an asymmetric pressure pattern here, which is caused by the propeller at the front of the aircraft. So the propeller not only pushes the air backward, it also introduces a swirl. So one side of the air goes up and one side of the air goes down, which means the air coming towards the wings is different left and right, which is why you get asymmetric patterns also in the surface friction that you see here. The blue areas, low surface friction. As you saw, if you follow the surface, you start to generate friction. If you don't follow the surface, it means you have low surface friction, but it indicates that you have separated airflow. Remember the golf ball, as soon as the airflow goes straight, in the wake you have no attached flow and you have low surface friction. These are the streamlines to illustrate how the air flows around the aircraft, how it gets pulled down by the propellers and so on. We have the same, but then for horizontal streamlines. So here you can really see that the overall air gets pulled down, it gets accelerated by the central propeller in the middle, which is the red that turns up. We also have a rough indication of wind noise. It's not very accurate because it's a steady state simulation, so it's just an indication. If you want to do this precisely, you need a transient simulation. And then we can also click the elements here, so we can analyze the propellers and just see how much torque, thrust and power they generate or require to operate. And we also calculate the propeller coefficients automatically. So coefficients, they indicate how efficient the propeller is, the thrust coefficient, the power coefficient, and so on. Then the last thing is the forces. So the forces, of course, we calculate the lift and the drag on the entire aircraft, but we also calculate the force on each individual component. So again, nothing manual was required to set this up. If you upload a model with 700 components, every component will get its own individual mesh, if it's large enough to be captured by the mesh, and then you can analyze the forces by just clicking on them. You can also download the full PDF report and so on. We can do the same with just isolated propellers to study the performance of a propeller. Now this is an interesting case. What we did here is, well, it's a long story, but I was walking around in the city. I saw an antique propeller, a wooden propeller from a World War II era plane. I found it to be really nice. Then we scanned it using photogrammetry. We built a 3D scan of the model, and then we just analyzed that model in Airshaper just to illustrate that we can work directly with 3D scans as well. And then we ran simulations, and afterwards what we did, we put the same model on a 3D model that we found on the internet of an aircraft, just to see how the performance of a propeller changes when you put it on an aircraft. Because analyzing the performance of a propeller in an isolated way is one thing. It's very interesting. You get to map all the characteristics. But if you put it on an airplane, suddenly there's something behind the propeller. So the air that you're pushing backward starts to hit the aircraft. And this provides a back pressure, which you again feel on the propeller. So weirdly enough, the thrust on the propeller can go up a bit if it's on an aircraft, but that doesn't mean you just gained thrust, because there's also extra drag on the aircraft, which is behind you. So in the end, of course, you have to look at a full aircraft to know whether the propeller is working well in combination with your aircraft. Of course, one of the main questions we get is this accurate? Well, our customers, they benchmark our solution. We can also benchmark our solution, but then of course, if we say, yeah, we did our own wind tunnel test, it's super accurate, you can imagine that not everyone would believe us. So we put data of our customers on our website where our customers did an independent study. And you can be quite sure that a customer is actually quite skeptical. They will want to see a delta between you and the wind tunnel test. And the basic assumption is that if there is a delta, it's because of your software. That's normal. That's how we respond to using something new and so on. So that means these tests were done with a very critical mindset. And still, we saw a very good correlation between the wind tunnel data, which is the blue one here, and the Airshaper data. This is the drag curve, so they changed the angle of attack of the drone and measured the drag and the lift for different angles of attack. Here the same for lift. This is a picture of the wind tunnel. This is an old picture of their drone. Actually, we're using or working on a newer one, which we cannot show yet, just as an illustration. This is another illustration. It's a fighter jet. We run non-compressible simulations, so we're limited to Mach 0.3, but this one was tested at very low speeds. So to test the landing and so on. What we see here, it's a bit difficult to read, but we see in pink the wind tunnel test data, and in black we see the Airshaper data. So we have a very, very good correlation actually between these values. If we then continue, this is a propeller validation. So this is a collaboration we have with Maislik, one of the leading propeller manufacturers, carbon propellers and so on, where we have a very good correlation between our code. So our best one is the light blue one. You can't see it because it's actually right on top of the wind tunnel data, which is the green one. It's only at the end that we start to see a discrepancy. And the funny thing is that actually the simulations are more accurate than reality, because at high advance ratios, that means the incoming wind speed is very high and the propeller cannot keep up. So the propeller starts to become like a blocking disk, which means you have blockage effects in your wind tunnel and you have inaccurate wind tunnel test data. Just as a tip, aerodynamics is very complex, very expensive in many ways, but there's nothing holding you back from trying this yourself. This is something that I did just to play around. It's an old Volkswagen Beetle. We did some tests on the Beetle with tufts. So this is, I just needed €5 for some tape and some wires, which I put on the rear window of the car. You may think, oh, it's a Beetle, it's very streamlined. I don't know how popular the Beetle is, but it's actually not streamlined at all. We saw before that if the curvature is too steep, the flow will let go. Well, the Beetle is one of those examples, especially when you have a disturbance like this on the window. It just destroys the airflow. So what I wanted to do is to see, first if I would measure the airflow, depending on how much these little tufts, or these are just small light wires, they will move together with the wind. And if there's lots of turbulence, they go crazy like this, and then you can see that you have detached airflow, turbulence, and so on. So I did one reference test where I put the camera inside the car to look outward, and I just plotted the minimum and the maximum of each wire, which is like a spread. And they were moving around a lot, so I had like a big spread. And then I put these vortex generators on there. I had to try a few times to get them right in terms of position. But as soon as it worked, the movement of the wires was reduced a lot. So just as an experiment, if you have a car, if you have like an object in the wind tunnel, of course you know about this technique, but it doesn't cost you much. Just go out there, film it, use a GoPro, whatever is. To me, it's very important, even though I'm working on software simulations. To me, the most important thing is that you really understand aerodynamics, that you feel the physics, that in your head you can start to look at something like an airplane over here and just see, oh, that's going to be a problem area. I think this is going to happen. To me, simulations are still a tool to build that understanding in your head. Not just running simulations, oh, okay, that's what the software says, but to really understand what is happening. If you look at some of these people in Formula 1, we also have someone from F1 Aerodynamics in our advisory board. Some of these legends, they can just take a piece of paper and draw something like a solution to solve a problem without running a single simulation. Of course, at some point it becomes really complex to still do this, but if you can get to that stage, I think that is highly valuable. And getting out there yourself, playing around, doing these experiments, feeling the physics, to me that's still very important. I hope that it becomes an asset in your career. Who uses our platform? Just some examples. This is the Red Bull Air Race. This was Matt Hall, Australian pilot. He also became world champion then. Not because of us necessarily, but they used our software to optimize some parts of the aircraft. This is quite crazy, by the way. They pull up to 10 Gs in their turns, which is truly insane. In Formula 1, it's maybe 4 or 5 Gs in the corner. This is where you would pass out. Some customers, Leoflight, they use our software. Bellwether uses our software to combine propeller thrust, forward flight, cruise flight, all of those things. Some automotive examples. Actually, I started doing aerodynamics because I had designed the car in my free time. So it was really cool to actually work on a project where we could build a custom car. So this client came to us with a base Lamborghini, and the question was, I want to go 300 miles per hour. And then we said, okay, let's get to work. So we worked closely with the designer, and we did the full aero package. Every single thing on this car was changed. So we did the air curtains at the front, we did the front splitter, we did wheel arch ventilation, air intakes on the side, the bottom or underfloor aerodynamics, we did the diffuser, many iterations, winglets at the rear. And then they were going for their first test, and the goal was to hit 420 kilometers per hour. Now on the first test, they already hit 447 kilometers per hour. So the thing has been built, it's driving around. And now we're modifying it a bit more to go even faster. We also do reverse engineering with our software, which, because we're compatible with very complex 3D models, which don't have to be watertight, we can work with models like this 3D scan. This is by a highly professional company. They take cars apart, up to 1,800 components, scan them individually, put them back together digitally, create a model, and then we just run a simulation on that model without any single modification. And then we can just benchmark the aerodynamics of competitor products in the market. Sample projects, if you want to just see some of the projects that I showed you today, or experiment a bit, just go to airshaper.com and click sign up at the top, or go directly to the app, to app.airshaper.com. If you create an account, the account is free. You'll be able to go to simulations and then to sample simulations or public simulations and browse through a whole number of simulations. The sample simulations are things that we did ourselves, which are non-confidential and we made public for everyone to see. When you click public simulations, what you see there are simulations by students from all over the world. So 2 months ago, we decided to offer free simulations, of course with a number of penalties, but you can experiment with the platform yourself. So that means if you create a free account, and please stick to one account because we do see when people start creating fake accounts. But if you create a free account, all accounts are free, but if you run a free simulation, first of all, your results will be public. So keep in mind that other people will be able to see your 3D model. So if it's confidential, don't do that. And you will not get the data on the drag and the lift. So it's mainly there to visualize the flow on your object. Nevertheless, it's a very nice way to experience CFD simulations, to see what the results look like, to see where you have flow separation, and so on your design. It's low resolution, but it allows you to just play around. And we have a bunch of videos. So of course, if you build a software product, you need to sell it. So one of our aspects is that we have invested heavily in building a YouTube channel. So that means we have over 100 videos already where we've interviewed cool companies. We've been to NASA 2 times in the States to visit some of their locations and research facilities. Saw the biggest wind tunnel in the world on their facilities where they can really put a full aircraft in the wind tunnel, went to the Air Force bases and so on, interviewed Airbus. But we also have plenty of videos on how to analyze the results of a drone, how to set up an airplane simulation, the Lamborghini stuff, race cars and so on. So if you're interested in both the theory and practical examples, just head over there. It's free. It's a YouTube channel. So if you have any tips, always welcome, of course. And that's it, actually.
Thanks for your very, very good presentation.
You're welcome. Yeah, of course.
혹시 질문 있으시면 손을 들고 질문해 주셔도 됩니다. 만약에 영어로 하실 수 있으시면 영어로 직접 하셔도 되고요. 아니면 이제 한글로 하시면 제가 설명드릴 수 있거든요. 자, 질문 있으시면
Hi, thank you for your presentation and really good plan for understanding the airline. My name is Yeongmin, and I'm a student.
Okay.
So my question is, how much can downsizing the aircraft or car to the experiment in like Yeongmin or your company? So because it depends on cost or
You mean the scale factor?
yeah.
Well, like in Formula One, it can be like 60 or 40% that they would use, or you can use a full car. Now, for cars, very often they would also use like a full-size wind tunnel, because many car manufacturers have invested heavily in their own wind tunnel facility. If you look at, this is already more than 10 years old, this data. The BMW wind tunnel, for example, that thing alone cost 130 million euros just to build, but they have it. And most of the manufacturers have a full-scale wind tunnel where they can actually run these tests on their cars. But still, yeah, scaled models are still being used as well. You have a tunnel here, you can also use it, but keep in mind it's a very small scale, so you need a very high velocity in theory to match it. You're welcome. Nice to meet you. So what was the last part? Is there any? What was the last part of the question? Oh yeah, to normalize any errors. There are ways. So we saw that there's a blockage factor. You can do corrections for blockage factor. That's not scale. If you work with scaled models, it's the Reynolds number, but it's also other aspects like the roughness of your object. If you scale your object, in theory, you need to scale the roughness on the surface. So if you have certain paint on your car, the roughness is different on the scaled model relative to the size and so on. So there are many aspects to it. But yes, you can get this to work pretty accurately. And sometimes, even if you deviate from your Reynolds number, it might still result in almost the right drag coefficient. What you could do, for example, if you would run a simulation on your scaled model, and on the full-size model, you can already have an indication, is the drag coefficient actually sensitive to scale or not? Because the drag coefficient can be quite constant in function of velocity. So it could be, for example, that if you test your car at 50 kilometers per hour and 100 kilometers per hour, that the drag coefficient is exactly the same. The same way, it could also be that if you use a scaled model, that you don't really introduce too many errors. But as soon as you go outside this range, where it does start to play a role, it's good to just try and quantify the effect of this. So for some applications, it's fine to use a scaled model. But if you scale an airplane by a factor 10, you really have to study the effects of the scaling. You're welcome.
Thanks for the very good presentation. It was really interesting as you could see real world applications, especially the formula cases.
Yeah.
So my question is that most of conventional safety software out there, they're employing various toughness models. So and
Yes.
each of them has pros and cons. So
Yes.
I would like to ask you what kind of toughness model your software is employing.
Yes.
It's not
Yes.
confidential.
It's not confidential. So we use RANS-based, so Reynolds average Navier-Stokes equations with K omega SST as a turbulence model. So in industry, in academia, but especially in industry, you have to find a balance between the cost, the accuracy, and the speed, typically. And the K omega turbulence model is actually quite a good balance between those. It is not always the fastest, not always the most accurate. That's the same for any turbulence model. They always have their pros and cons. In our case, we want to offer an affordable solution with yet accurate results. So we saw that with our validation, we can be actually quite accurate. We also use wall functions, for example. That's also another big question or a big choice you have to make. Because the boundary layer that we saw, you can either resolve it by having very, very, very small cells and calculating every small bit, or you can have large cells and use what we call a wall function, which is a mathematical function that says, based on experience, well, we know this is the velocity profile, just use this, which is true in most of the cases, but always, not always. So there is also some deviation that you introduce. So to come back to your question, yes, K omega SST, which is not the most advanced turbulence model, but as we saw, we can actually get quite accurate. And in return, you actually get a solution which in some cases is 10 times faster and more affordable than another turbulence model, or an LES or DES approach, for example. So it depends on what you're looking for. If you're an aircraft manufacturer and you're looking at a very critical stall regime for a large aircraft, you're going to have to go to a very, very, very accurate model to solve it. But if you're working on industrial applications, cars, smaller aircraft, drones, eVTOLs, and so on, it actually shows very good correlation. You're welcome. Yes. That I wouldn't know. I would imagine it also works with just a rectangular grid. Probably it also works. Maybe it has to do with the way they produce it or the structural stiffness. Or maybe it's the ratio between the volume and the surface. You don't want to introduce too much friction. That I wouldn't be able to answer. Sorry. Yes.
As I know, there is a large amount of options in OpenFlow. And
Yes.
as I know, that your solution is based on OpenFlow.
Yes, correct.
Is there any plan to employ the options into your software?
You mean open foam options to make them available in the software?
Right.
Actually, no. Because our entire philosophy is that we automate everything to provide you, first of all, with a very easy workflow and with a very high level of consistency. So we want that if you come back 6 months later, or within your company, 5 different people are running simulations, we want everything to be comparable. What you would often see is that when I was doing consultancy myself, before I founded Airshaper, when I would do a simulation on exactly the same car, if my colleague would do a simulation, the output is different. Even if the hardware is the same and the software is the same, because we have different habits, different philosophies on how you should make a mesh, how many iterations you need, and so on. So we want to control that, not because we're control freaks, but because we want to guarantee consistency between the simulations. Also, we want to provide robust solutions. We want that whenever a customer uploads something and runs the simulation button, that the result will be there. If we open up settings in OpenFOAM, we do have a number of expert settings for our enterprise customers. But if you allow to change the viscosity, for example, and suddenly someone puts a viscosity which is 100 times higher than air, it might crash, for example, or might be completely unrealistic. And then you lose track of why something failed. You have to dive into the case and, well, okay, but this is wrong. And our philosophy is that we take responsibility for a reliable outcome. The other software packages are equally valid. I mean, I really like ANSYS, I've worked with it, Star CCM, SolidWorks, and so on. Their approach is, here are the options, you set the options right, and then your result will be good. If you set them in the wrong way, your output will be bad. It's a perfectly fine business model. They get all the freedom, but it's the user who's responsible. In our case, we take responsibility for the quality of the output. And we can only do that if we take that in our control.
This is not a question, but can we have the file?
I can have a look afterwards and then see if I can, it's quite a big file, but with all the videos, but yes, that should be possible.
Okay,
Yes.
if I can get that file, I can share that to other students and the other people.
Yes, yes.
다른 질문들이 대답. The question is we saw some slides to import the geometry from taking a picture from sorry.
Oh, the propeller blade.
Yeah.
Yes.
Can you please explain what the sensors were?
Oh, yes. Well, this is not related to our software. This was a free time project. So I just used the camera. I took many pictures from different angles, and then I used some open source software that I found online, which is called photogrammetry software. That's the general term. It's a principle where if you take pictures from different angles, the software can actually reconstruct a 3D model based on 2D pictures. And that's the way we did it.
You just used the cell phone camera?
Well, yeah, it was a different camera, which was a bit more precise, but you can do it with your cell phone as well. Yeah.
So you used the camera and the software?
Yes. Yes. You're welcome.
다른 질문들이 혹시 있으시면 워터 이메일 주소를 공개를 할 테니까 그쪽으로 직접 질문을 하셔도 되고요. 아니면은 뭔가 질문하기가 좀 어렵겠다 싶으면 나한테 주면은 내가 질문할 수 있습니다. 그리고 만약에 여기서 지금 그러니까 오늘 설명했던 내용들이 다 이제 유시협학이나 아니면은 이제 컴퓨터를 시뮬레이션하는 내용들이 텐데 이게 다소 학생들한테는 좀 어려운 내용일 수 있잖아요. 만약에 이 내용들을 좀 들어봤는데 궁금한 게 생겼다라고 하면은 직접 질문을 하셔도 되고 아니면 저한테 질문을 해주시면 그러면은 내가 어느 정도 설명을 할 수 있을 거거든요. 그래서 편하게 질문을 할 수 있는 그런 기회를 하고 있습니다. 네, 그러면은 한 1시간 반 정도 되는